So now we are going to look into if we want a numerical scheme that can solve this kind of differential equations and resolve shock waves correctly, what do we need? To answer that question, we first have to analyze what is the correct behavior of this type of differential equations around shock waves, right? Okay, so the behavior of this kind of differential equations near shock waves is actually a little bit analogous to the behavior of the differential equation around actually smooth regions. So let's actually start with the behavior of this type of differential equations around smooth regions. So remember, if we have a constant u, this type of differential equations, right, has an analytical solution. What is that analytical solution? So if I have plus a constant u, w would be equal to what? W0 of x minus ut, right? So what that means is that if you draw a diagram, vertical axis being time, x-axis being space, what is x minus ut, right? If you put any point x and t, what is x minus ut? X minus ut is basically you draw a slope, you draw a line whose slope is actually 1 over u. Okay, and you draw a slope backwards. So basically the vertical axis is going to be t, and the horizontal axis is now going to be ut. So x minus ut, if this is xt, x minus ut is this point. This is now x minus ut, right? Agreed? So the analytical solution of this constant velocity advection equation is actually basically saying that for any point in x and t, I will just backtrace onto the initial condition, onto t equal to 0, and find out what is the initial condition value at that point. So that's it. Okay, now if you look at the behavior of this differential equation, let's just plot not the end, but maybe, let's see, t is equal to 41. Let's choose 20. Hold on. Hold on. Okay, so just look at, for example, this the behavior of this differential equation. Can you see something analogous to what we said before? Okay, can you see something analogous here? Yes, actually, maybe it's a little bit hard to transfer the mental gymnastics between a plot of w versus x and a plot. So basically, you have to transfer animation, right, in 2 dimensions into a 3-dimensional plot where one of the dimension is time, right? So you kind of have to rotate the plot this way so that the solution goes out of the board, and then put the animation as if it's advancing in time. So basically what happens is, if this is the tip of the wave here, the tip of the wave is going to go to here, right? Well, if the bottom of the wave was over here, then the bottom of the wave would be traveling like that. So again, we have constant slopes in the solution space on which the solution is a constant, right? So we have straight lines in the xt space where the solution is constant. That's basically saying that if you track the same height on the plot above, the advection speed would be constant. If you track the tip, the speed of the tip is going to be constant. If you track the bottom of the speed of the bottom is going to be constant. If you track halfway between the top and the bottom, the speed is also going to be constant, right? But their speed is just going to be different. So yes, so basically, if you have this if you have the blue equation, so plus u of w, okay, it's the same thing except for u is now a function of w. So that means if I have another x and t, the wave may be going this way, right? So basically, for the blue equation, w at any x and t should be equal to w0 at x minus u of actually the same w times t, right? So of course this is not an explicit formula for you to evaluate, because the right hand side actually contains the left hand side, right? So you kind of need a nonlinear solver to solve this equation. Of course, because the equation is a nonlinear equation, right? Do you see like what this equation is about? So this is the advection speed, but like there is a unknown on both sides of the equation. Everything else is known, right? So if you want to evaluate this analytical formula, you have to, you have to use a nonlinear solver. But why is this a solution to the differential equation? Because if you take partial w, partial t, right, it's actually equal to use chain rule on this, right? So if you use chain rule on this, what you get is well, let me actually figure out a slightly better way to do this. Okay, so let's actually partial w, partial t. Yeah, let's just go through this. So if you use chain rule, you get two terms. The first term is dw0. Oh, let's first do it very carefully. dw0 dx times the derivative of this whole thing with respect to t, right? Okay. So the derivative of the whole thing with respect to t is has actually two terms. One term is minus u of w, which is x and t, times the derivative of t to t, which is 1. The other term is minus basically du dw times partial w partial t times t. Right? Agreed? So this is the second term, is because this u now also depends on t, right? Okay. On the other hand, partial w partial x can be computed using the same way. All right. So this is dw0 dx. Also, I have two terms. The first term is dependence to this x, which is actually 1, right? The second term is because now the u also depends on x, and that is minus du dw partial w partial x times t. All right. So now we see that why the differential equation can be satisfied. So if you multiply the second equation with u, okay, let's use this. If you multiply this with u, you get a multiplied by u here, and you also get a multiplied by u here, right? So the first, and if you add them up, this is going to cancel, okay? And basically what you have is an implicit formula saying that I have dw dt, dw dt plus u times dw dx. If this is 0, this is also cancelling, and this is also going to be 0, right? So basically you have what you ended up is the differential equation on the left hand side, and then equal to the differential equation multiplied by something else on the right hand side. Right? And as long as that's something else, as long as du dw times t is not du dw times t times dw0 dx is not equal to 0, or is not equal to 1, the differential equation should be satisfied. Right, so if you add them up, what I get is the differential equation is going to become dw0 dx times minus du dw times t times the differential equation. All right, so basically we can see that yeah, so that solution should make the differential equation equal to 0. All right, any questions on that?